So if you've seen me last year, I'm the machine learning person. And so, like I said in my introduction, this is going to be about, this is a case study about how I went about to write a system that will learn stuff. So that's the short explanation. I would like to walk around more, but apparently I have to stay close to the microphone. So this is me. This was the good old days. That was last year at the JSUnconf. You can follow me on Twitter, on GitHub. Those are the platforms that I actually look at if you want to catch up. So during my daytime, basically, I'm a software developer at Datenfreunde. We're a startup doing a bit of JavaScript, bit of Python, machine learning, and we have an app. So if that's interesting for you, you can talk to me about that too. And but by night, I'm a machine learning enthusiast. So this is my hobby, basically. All right, let's talk about the game. So if you haven't Googled it yet, even though I asked you to, this is Threes. That's the original game, basically. And as you can see, basically, the idea is to merge 1 and 2 or multiples of 3. And as soon as you merge them, you get a higher value, you get the sum of those values that you've merged. And I don't know what the goal is, actually. I guess it's to play as long as you can. And basically, you have 2 inputs, left, right, up, down, and then every time you swipe left, you will swipe the entire board to the left. That's the basic idea. So Threes came out, and then suddenly, for some reason, I think someone implemented the simpler version of it, open source, and then suddenly like all kinds of clones came up. The original is 2048, and there are all kinds of 2048-like games. I think the most popular was 1024 or 1024. But there are also like this one, which is, it's pretty hard to know which one you have to merge and what it's going to be afterwards, but I guess it works. So, but I'm going to be talking about the simplest implementation, that's 2048. That's just the basic. You can check it out on GitHub, and it's free, and it runs in the browser. Yeah, I think the hardest thing, actually, while working on it was not to get distracted by the game all too often, because you're just like, oh, I'm going to try this out, and suddenly, like 10 minutes later, you realize I've been playing this game for 10 minutes now. I should really get to work. All right, so let's look at the rules, quick overview, just so we're all on the same page. We have a 4x4 grid. That's all seen that. And each turn, basically, you take an action, which I call alpha here. And alpha is 0, 1, 2, or 3. So it's one of this set of numbers. And so you take this action, and after you've moved, a new tile will add it to an empty space. And there's a probability distribution, so there's a 90% chance that the new tile is going to be 2, and there's a 10% chance probability that the new tile is going to be 4. So every time you move, you get a new tile. If you merge 2 tiles with the same value, then you will get 1 new tile with the value of the sum of those 2 tiles. I think you've seen that. I just written it up once more, so you remember it. All right, and then, so basically, there are 3 measurements of how well you're doing. You lose when there are no more moves possible because the whole board is full and you can't move anywhere to merge anything. You win when you have 1 tile with 2048 present, or 1024 in the other game, or like the rainbow dog with the dog game, I don't know. And then there's an additional thing that's called the score. And the score is basically every time you merge 2 tiles, then the sum of those 2 tiles is added to the score. So basically, every time you merge something, your score gets updated, it gets higher. So these are the basic set of rules, and so I basically just started. I was thinking, okay, first thing, the most important thing is the name. Alpha2048, of course, it's a pun. It's a reference to AlphaGo. That was like the most important thing, and once I got the name, I was like, okay, I'm all set now. The second thing was that it has to be JavaScript, because I really like JavaScript. It's easy to set up. It just runs. You can run it in the browser. You can run it with nodes. So it was just just to simplify things, basically. And then the other thing was that it needs to be supervised. So basically, supervised learning means that I'm teaching my machine something where I already know the correct answer. I already know what I want my machine to predict for me. So I'm telling my machine, okay, if you get this set of inputs, I'm expecting this output. The other thing, unsupervised learning, you just tell the machine, do you see a pattern here? But I don't know the pattern. So supervised, because we know when we get to 2048, we win. All right, so I started with a library. Those of you who've seen me give the talk last year, you already know it. It's called Synaptic. And it's blue because it's a link. And Synaptic is a neural network library for JavaScript. So I don't know, neural networks, I think you've heard of it. I'm not gonna explain it. It's just, it's doing machine learning magic. That's all you need to know now. So what Synaptic does is it does classification, which means it classifies. So it's in the end you get either 0 or 1 for whatever you want to predict. So you can't predict numbers per se. That would be called regression. So you can't predict, like, if I make this move, what will my score be? So it has to be something, the thing you want to predict has to be something between 0 or 1, or true or false, respectively. So, yeah. And then, of course, I have prior experience with Synaptic. That's also a link to the project I showed last year. It was a soccer result predictor thing. So that was basically the reasons why I started with Synaptic. I already knew everything, and I had a pretty good idea what I wanted to do. So, first iteration. So first, I was basically trying to find out what is it that I want to do, actually. What is it that I want to teach my machine, or what is the first step I need to do right now? So the first step, I thought, sure, gather data. I need some kind of data. And the idea was that basically I try to predict the best possible move for every turn, basically. So the way I went to do that was to simulate all actions. So if I have a board state, let's say that's the first state that I'm starting to play the game, then I'm going to simulate all possible actions, so 4 of them. And then afterwards, I'm going to check, did the score increase? So basically, when I swiped left, did the score increase? When I swiped up, did the score increase? Blah, blah, blah. And then, after I did that, I actually just made a random move for the game. So first I simulate, and then I just make a random move. I could have, of course, just checked where does the score increase and make that move, but I wanted to start random because I wanted to see how well my algorithm basically performs against just randomly moving. And you would be surprised, if you do random moves, you will get to like 256 every 10th time. So it's like, you can just play it randomly, don't look at it, it's pretty good. So this is basically what my data set looked like. Board state was my input. That's a serialized state of the board. So I just have like, I count from left, upper left to down right, basically, and then it's 0 to 0, I don't know, 1, and then just goes on like this. It's 16 different elements, of course. And the actions, those are basically bools that say if the score has increased after making this value. So basically, I'm saying I have this board state right now, and for each action I took, this is what happened to the score. 0 is the score didn't increase, 1 means that the score increased. So I guess that's pretty clear what I mean. Yes, okay. All right, so I simulated like 100 games or so, and then I was like, okay, I have data now. I think that's gonna give me like a good indicator whether my idea is working or not. So, second iteration. This time, the goal was to compare the trained network with the untrained, or with the random decision maker. And so, of course, the first thing I needed to do is train a neural network. And basically, the way you go about training a neural network is just give it the input, give it the output, and then let it run a lot of times, so it will slowly, hopefully, recognize the pattern behind the stuff you want to predict. And then, so after I trained the neural network, I will use that network to predict whether the score increases or not for each of the possible actions. And then in the game itself, I'm going to make the move where the probability that the score will actually increase is the highest. That's pretty straightforward. So I'm not gonna show you any data on this because it was pretty boring, and it wasn't like there's nothing to see. I just saved them into Couch and like came up with some clever metrics. But the conclusion, basically, to make it short, was that it didn't work all too great. I think it was a little bit better than doing it randomly, but there was no, I couldn't see that the game is actually being played in a meaningful way. I don't think the algorithm actually understood what this game was about. And I think the reason why it was like that is that it focused only on the next state. So it was basically only predicting whether the move will increase the score for the next state, but it didn't have like the foresight to check whether this will be good for the whole game. So what I needed was some kind of machine learning method that had more foresight, that would be able to see that it's not only one move, but it's like a series of moves, and then at the end, that's the most important state, basically. Did you win or did you lose? All right, so I looked around a bit. So basically, I had to ask myself, do I want to keep using Synaptic and this classification network and try to come up with better inputs and stuff like that, or do I want to scrap it and do something completely different? And thankfully, my husband, who wanted to do the ghost AI thing, but then he didn't, he helped me a little bit with it, and then he introduced me basically to nice methods that were perfect for my use case. And basically, it's about reinforcement learning. Reinforcement learning, as the name already says, is basically that you, instead of giving your system a value at the end, you will just tell it, this is slightly better, or this is slightly worse. So it's not like a full, like a 1 or a 0, it's just like, oh, this is pretty good, or this is not as good. So reinforcement learning makes use of like 2 or 3 different strategies, basically. And the first one is called Markov decision process. I don't know, maybe you've heard of the Markov chain. So Markov chain is basically, it is a defined chain of states and actions. So you have a state, and that state has one possible action, then it will lead you to another state, and that state will have another possible action. It's a stochastic model, so there's like the one action that it's gonna take is like the one that is has the highest probability of being taken. But this is one defined chain, and there's no decision making in it because the chain has already existed from the beginning. And the Markov decision process is basically an enhancement of that chain. So if you take a decision process, you have the rewards in the end, and you have possible directions, and the decision process basically decides which action it's gonna take. Or if you say it the other way around, if you take a Markov decision process and only give the reward 0, and you only have one action, then it's the same as a Markov chain. That's basically the thing. Then the other nice thing for reinforcement learning is that it can deal with a delayed reward. So you can have a lot of states and actions and then give a reward at the end of the chain, basically. That's nice, because then you can tell your system that this is like a chain, and then in the end, the end is the thing that actually matters. So this is actually perfect for games, or for my case. And so the one thing that is basically the challenge of reinforcement learning is exploration versus exploitation. And what that means is that, so on the one hand, all the experience that your machine gets is basically from the machine playing. So it plays, and while it plays, it learns. So you want to have a lot of different kinds of data sets, so it will learn new stuff, learn different ways to go. But on the other hand, you also want your machine to do the best possible moves that it knows of. So you got to balance those things. Like, just don't be too random, but also don't only stick to the stuff you already know. All right. Then there's another machine learning method that's more, it's like more concrete, and it's also something that is basically perfect for my use case. That's called temporal difference learning. And the thing about temporal difference learning is basically that it knows that there is a state in the end, and there are states and actions that precede this end state, and it will slowly learn how those states before can influence the state in the end. And it also gets that maybe like the begin states are pretty important, which moves you make, but the ones toward the end are not as important anymore. So those are things that the temporal difference learning deals with. There's also two strategies you need to understand. The first one is dynamic programming. So it utilizes dynamic programming, which basically just means dividing your big problem into sub-problems. So you have like this whole chain and you're dividing it into smaller units of problems to solve. And the other thing that it makes use of is called the Monte Carlo methods. So Monte Carlo method is a heuristic search tree, more or less. You have like a tree where you say, okay, from this state, I have 4 different actions, and those will lead me to this state, and so on and so on. And at the end of the tree, you have values, which are our rewards. So every time we tell our algorithm to predict something, it will look into the tree and look basically, do I have a reward for this exact scenario? If not, I'm going to choose a scenario that is close to it and gives me a high value. So basically what temporal difference learning does is it combines a heuristic like search algorithm with machine learning, because if it doesn't find the exact reward, it will approximate it by the other data it already has. That's also how AlphaGo did a lot of stuff. All right, so I Googled, like any good developer would do, and what I found was a library called Reinforce.js. Yes, there's actually a reinforcement library for JavaScript, which is pretty awesome because it also runs in the browser. And Reinforce.js was written by a guy, I forget his first name, but his last name is Kapati. And he based it on a paper, on a scientific paper, where people solved Atari games with reinforcement learning, with temporal difference learning, Q-learning. And that's pretty cool. So I was like, yeah, okay, this is perfect. And it's also the only reinforcement library for JavaScript, so I didn't really have a choice. All right, so the code that I'm going to show you that's basically the code. So you have the state that as before, it's a serialized state. Then you ask the agent is from the library, you ask it to act on this state, and the agent will return an action. This action is 0, 1, 2, or 3. And then you do the action. It's like this is hidden in the calculated reward state. Basically, you take the action, and then you will give it a reward and say, learn from this reward. Of course, like I said, this is one state, one action. You can do a lot of actions and then give a reward in the end, like I did. I gave my system a reward at the end of the game. So basically, when I use this, everything that I have to do, it boils down to what reward should I get. Like the whole model stuff is basically all in this reward. That's the only thing I need to take care of. So, okay, I'm working in iterations because that's the easiest for me. So first iteration, I decided let's do the simplest thing, just give it the score as a reward. So I don't need to implement anything myself, and the score, like I said, it's better the more you merge. So that's a pretty good indicator. All right, yes, this is my Grafana, and as you can see, there's really not that much happening. If we check the average, it's really not, there's like, yeah, it's higher here on average, but then it drops down a lot. So there's not really like learning intelligence that I could actually see there. So I was like, okay, I tried it. It doesn't work that great. Let's just try to find another reinforcement value or reward value to see if there's like something better. Okay, so second iteration was basically the task of finding a better value. Because I believed in the library, I thought it was the correct library, just my reward wasn't that great. So I came up with this thing, tile rating, and the tile rating was the sum of all values divided by the tile count, and of course everywhere where there's no tile, in my serialized array it's 0, but there's actually no tile. Those of course don't count, otherwise you always have to divide by 16. So what's different between the rating and the score? If you, oh, this doesn't, oh, sorry. No, why isn't this? Okay. Okay. Well, this was working very well. So you didn't see any of this, of course you don't know. So when we start, let's say this is our starting situation, and then this is our board. We have a score of 0 because we just started the game. The rating is 2.5 because we have the sum of the tiles is 10, and we divide it by 4, that's 2.5. When we now make a move to the left, let's say this is the move to the left. The two upper 2s have merged into a 4, and this 4 that has a green frame is the new 4. So this is the tile that's what was added after the action was taken. So that's the new tile. What we have now is we have a score of 4 because we merged those 2s, and we have a rating of 3.5. So okay, rating goes up when you merge something, and it also goes up when new tiles are added. Now, if you, for example, instead move down, what you have now is that the 2s were not merged. They're like the 2s in the bottom row, and the 4 is new, of course. And now this time we have a score of 0, and the rating is 2.8. So the rating has changed, the score hasn't changed. So that was basically my idea was, well, it's a little bit different. And so maybe that might be better for some reasons. I wasn't entirely sure, I just wanted to try something else. Also I was thinking, if you don't win, because in the end it's about, do you win the game or do you lose the game? If like all the games you play are basically all losers, then there's really no point in giving the reward back because it's always the same reward. I was thinking the next best thing is the highest sum of tiles, but with the lowest number of tiles. That's basically if you just look at one single state, one that has like a higher value but a lower number of tiles would be better than a board with a lot of numbers, but they're all like 2 or 4. Okay, so this was the idea behind the rating. I tried it, it wasn't that great. It kind of looked like the score before, so I tried other things, and I came up with this, where the reward was basically the score divided by the average score times the rating divided by the average rating. And the average was taken from the last 100 games, so it was not the complete average, it was just the last 100, if there is a tendency so that we can use it. All right, so then what I was seeing there was basically the yellow line always looks like it doesn't move, but that's because the values are pretty high up there, like there's a 5.5 almost. So, but if we look at the average, okay, I was faking a little bit because I increased the time square. It's like 1 value per hour. But that was just so I could see, is there anything happening? And it looks like, actually, there is some intelligence there, like the score does go up over time, which could be an indicator that we're getting better. But I'm not pretty sure, because as we've seen before, sometimes there is like a really high peak, but then it like drops down immensely. So I would have to run it even longer. I used to run it during the night. I thought that would be enough, but I'm not entirely sure now. So I'm gonna try for a longer time, maybe train for a few days. But that was something where I thought, okay, this reward seems to be working better than just the score, so maybe I leave the reward for now and then try something else and then see how that works. And so I did a third iteration. This is also not working. Okay. I did a third iteration where I played around a little bit with the meta parameters of my system. What I did was decay the epsilon over time. And the epsilon is the value for the exploration value. So if you have a high epsilon, you do a lot of random moves. If you have a low epsilon, you just do the moves that you're comfortable with, that you already know. So if you decayed over time, it means at the beginning you do a lot of random moves, but the more games you play, the more you stick to the ones that you already know. And I thought this might work pretty well maybe, because then I don't go all over the place. I already have the stuff that I know, and then just try to go that path. Also, it was recommended in the documentation of the framework. Okay, so how did that look? Let's take a look here. That looks more jagged, right? There's more stuff happening. So yeah, I'd say it's fine. It's amazing. Like, looks good, right? Yeah, of course. It's perfect. I won. So yeah, it looks pretty nice, but so maybe you didn't notice it. When you check the total scores, you see that maybe there is a tendency moving up, but overall, the overall average is a bit lower than if you just return the score as reward. So there is learning, but it's starting from a worse point than if you would just give it the score, which might be okay, because over time you will reach like the best possible point, but maybe you will never reach it. So, but I'm pretty confident that this was a pretty good run. So this is how far I've gotten, basically. Yeah, I didn't really win anything, but I learned something. I looked into it and I learned something, and came to a conclusion. So what I saw is that it seemed to be learning in some ways. So it seemed that there was like a tendency of the score going up over time, but we have a few problems, and I think I'm not going to be able to fix it with this particular framework, with this particular system. The one thing is that the board size is kept. There's 16 tile spaces, and after a time, it just becomes very crowded on the board, because you always have to have like a 512, and then you have a 256 next to it, and you need another 256 to merge those, to merge the So you need a lot of tiles laying around, and it gets really crowded, and it gets harder the higher you get. And it could be that just at some point the system just can't handle it anymore, because it just doesn't know where to put all the tiles, basically. The other problem is that my input is flat, so it's a one-dimensional array, but the board is not one-dimensional; it's two-dimensional. But for this library, there was no way to input multi-dimensional inputs, so I had to go with that, and I could imagine that my system just didn't get that like element number 0 and element number 4 are like you can merge them when you go up or down. So this was something that the system would have to learn implicitly, and I'm not sure whether it got there actually. And so the other thing about reinforced JS is that it has one hidden layer hard-coded. And I looked into the library, and I was thinking about like changing it, but then like stuff broke, and I was like, yeah, no, I'm not gonna do that. I'm just gonna go with what I have and just, yeah, hold on tight, basically. But I heard the guy is gonna be in Paris, I think, when I'm gonna be there too, and then maybe I can meet up with him and we can like pair program it or something. That would be cool. All right, so what's next? What will I do next when I'm get around to it? I can play around a little bit with the meta parameters. There are lots of meta parameters that you have to give your system. Those are the parameters. So epsilon I already explained, right? So low epsilon means not as random, high epsilon means very random. There's this gamma thing that's also some kind of greedy. So if you have low gamma, that means that you try to get the best possible reward instantly. And if you have a higher gamma, you'll be fine with doing a lot of stuff to get a higher reward in the end. So that's something that you can play around with. There's the learning rate, which you can just try and error and try to find the best thing. There's the experience size, you can make it bigger, whatever. There's all kinds of parameters, and you can, if you want to get more into it, you can check out reinforced JS, and they're explained in a nice mathematical way, which I didn't include because it's kind of complicated. What else? So I was thinking to switch to Python. Python has a lot of nice machine learning frameworks, and I would be able to just do more, to introduce more layers, to try around a little bit. So that could also be possible, but then I couldn't run it in a browser, so I haven't really decided on that yet. But one thing I could do is something called convolutional network. And the convolutional network is basically a way for me to tackle this flat input problem, because in a convolutional network you could have 4 different nodes, and each node gets like 1 row, or you have 8 different nodes, and then you have 4 for rows and 4 for columns, and they will give all their values that they calculated and give it to the next network, so that you can actually have those kinds of relationships, and the horizontal relationships and vertical relationships, and the system will learn that. Yeah, that's basically it. So that's basically what I did, and there are some links if you're interested. So the first one is open source 2048. That's the game. Then there's this. Oh, nice! I didn't know this. So this is a paper where someone already tried to do deep reinforcement learning with Python for the 2048 game. I think he just rewarded wins with 1 and losses with 0, and said it didn't work so well. So you can look into it, what he did, and it's pretty interesting, actually. Then there's this introduction to temporal difference learning. That's more of a scientific paper, but it's still, you can still understand it. Just for, if I didn't explain anything too well, then maybe you can look it up there. And then, yeah, icons, presentation, reveal.js, great. So, live demo. So I will show you stuff that I will let it run in the backend. I'm not gonna promise anything. I don't think it will do anything, actually. But it's very hypnotic, and it's nice. So, I don't know, wait. Load, start. Okay, so if you have any questions, now's the time. Thanks. So I know, yeah, it's really hard to actually, like I said, it's the hardest thing. And then you start the bot and prepare for bed, and then you sit in front of it and just oh yeah, move it to the left. Yes, you moved it to the left. Does anyone have any questions though? Yes.